So here, I'm not going to prove it, but I'm going to discuss how we can prove that the constrained egalitarian rule, for example, satisfies claims monotonicity. So the same property, a different rule. The constrained egalitarian rule goes as follows. For any claims problem CE and for any individual I, the constrained egalitarian rule, which is denoted by CE sub I, under this claim problem CE, so there are too many C and E's, I know, is equal to a minimum of C1 CI divided by 2, comma lambda. All right, so very much like the constraint equal awards rule, but this time we actually care about sort of the half of the claim, and this is true if, however, the surplus E is less than or equal to the entire sum, the half of the claim sum. All right, I from 1 to I think I should use J from 1 to N, because this I is for individual I, and this I is an index. So right, so it's J. Let's call it. I mean, I hope it doesn't confuse. It shouldn't, but just in case, let me put J there. And then otherwise, I mean, if the E is not that small, if it is bigger than the sum of the house, well then it gets ugly. The constrained egalitarian awards rule is going to give me the max of CI divided by 2, comma, min of CI lambda. But whatever it is, we have to satisfy the following. Summation J from 1 to N, CEJ has to be equal to E, and it has to be feasible. I mean, you have to choose lambda, either in this case or in this case, doesn't matter, but you have to choose lambda such that this equality holds, because otherwise it's going to be not feasible, okay? So, in this case, obviously showing that this rule does satisfy claims monotonicity is harder. Well, why? Well, because this is a step function. If this holds, well, then your function takes completely different form. Otherwise, it takes completely different form. All right, so each form you need to show that whether it holds this or this, you have to show that claims monotonicity work. Well, actually, this part is easy, right? Well, why? Well, if your surplus E is very small so that this satisfied, well, then this term is very similar to constrained equal awards rule. Remember, in the constrained equal awards rule, I had this term, lambda, I'm sorry. So here, the only difference is I have the half of CI. So what does that mean? That means the proofs that I already gave you in the constrained equal awards rule, showing that it does satisfy claims monotonicity, exactly the same logic should hold if E is small enough, all right? Because again, the only difference is CI divided by 2. So you only need to modify your proof, and instead of CI, just put CI over 2. But be careful about it, because the inequalities are going to be slightly different, obviously. But the logic should be definitely the same, no different. All right, well, but again, this rule is more complicated than the constrained equal awards rule. What if this is the case? Meaning if E is larger than this sum, then it's going to be this term. Okay, well, clearly the proof is going to be different, but sort of the big picture logic is going to be probably the same. All right, what does that mean? That means I have two different problems, right? CI, C minus I, E. Remember, I'm checking claims monotonicity. So this is problem, the initial problem. So in this case, we have CEI for everyone. And then I have CI prime, C minus I, E. So only player I's or individual i's claim has increased. Well, in this case, we're going to have CEI prime, right, for everyone. Or maybe I should call it J prime for every J, Okay, so in this case, I'm going to have some lambda. In this case, I'm going to have some lambda prime. So probably lambda prime here is going to be different than lambda here. Okay. Well, what else? Well, remember, in order to prove that this rule satisfies claims monotonicity, we need to show this. CE for player I, whose claim has increased, so I don't care about other J players. So CEI prime has to be greater than or equal to CEI. All right? Well, again, proof by contradiction. What does that mean? That means there's going to be some player I who has a higher claim. All right? Let's call this time assumption 1, but this doesn't hold, so therefore it's strictly less. So this is assumption 2. So I have 2 assumptions. Well, then, by using these 2 assumptions, I need to deduct some facts and then reach contradiction for each and every one of them. Well, how do I do that? Well, remember, open this up. So what does that mean? CEI prime means? Well, it means the following. Remember, I assumed E is less than or greater than this term. So therefore, I'm going to be looking at here. So it is going to be max CI prime 2, comma, minimum of CI prime lambda. So this term is less than, sorry, I don't have any space. Let me write it here. Max CI divided by 2, min CI lambda. Oh, lambda prime. Don't forget lambda prime. I'm sorry. Okay? Well, with exactly the same reasoning, again, the logic will be similar. What I need to do is the following. Remember, by feasibility, we have to have CEJ, j from 1 to n, is equal to j from 1 to n CEJ prime, which is equal to E, right? And so by using this, try to open this up as I did in the previous proof, meaning just write them as player I's CEI plus CEJ, everybody else, J not equal to I. E has to be equal to the same thing, CEI prime plus summation J not equal to I, CEJ prime. And so, you know what? Because this guy is greater than this guy, well, then this guy must be less than this guy, all right? And then here, because these are less, you will probably get, again, the same thing. Is like the lambda prime has to be greater than lambda, all right? So the same inequality. And then come back to this one. And here, obviously, there's going to be much more cases you need to consider. But, you know, that's a good exercise to do a case study. So for each case, you have to probably conclude that lambda prime is greater than lambda, which contradicts what we claimed here, or the other way around. I don't know which one is true. But nevertheless, analyzing, you know, different cases here are going to lead to a contradiction, which you probably had achieved here between lambda prime and lambda. But obviously the things are going to be different here. So remember, in the previous proof, I had very simple case, like minimum CI lambda. So I had 2 cases. If CI is greater than or equal to lambda, and or if CI is less than lambda. Here, obviously, I have more cases. Well, why? Well, one case is that CI over 2 greater than min C lambda, because in this case, this is going to be equal to CI over 2. And then I have to compare it here. And then the second case is going to be, well, the min of C lambda is, CI lambda, I'm sorry, is greater than CI over 2. Well, but this is going to lead to another 2 cases, because the minimum of CI lambda, which one is actually the min? Is it CI? Is it lambda? So that's going to give me another 2 cases, all right? So therefore, what I want to say is that there's going to be much more cases here rather than 2. Does it make things complicated? Not really. If you just go in an organized fashion, you'll see actually the logic is almost always the same. Okay? Well, one more thing before I conclude. Obviously, you shouldn't miss that. Let me get some space because the board gets too complicated to me, crowded to me. So here, when we increase Ci to Ci prime, so that Ci prime is greater than Ci, okay, what we do is that this Cj divided by 2 sum is now become Cj prime divided by 2, all right? I mean, actually, it's going to be this. Ci prime plus half, Cj divided by 2, j different than I. Okay, so here what do I have? I have Ci divided by 2 plus sum Cj divided by 2, j different than I. So what do I know? I know that this term and this term are exactly the same because everybody else's claim will stay the same. Player I's claim increasing, and so half of it will be greater than, and so this is what we have. Well, remember, this case is when E is less than. So when I increase Ci prime, so when I start in this case, and when I increase claim of player I will remain in this case. However, when I assume this case, the E is going to be somewhere here, right? It's going to be greater than or equal to E. But is it greater than this or less than this? So that is important. If you want to do this analysis, you need to assume that E is not only greater than or equal to this, but also greater than or equal to this. But what if E is in between here? What does that mean? That means initial problem, the initial Ci and E falls into this category. And then once I increase player I's claim, well, then the problem jumps to this one. Is it possible? Of course it is possible. It's one of the possible cases. All right? So therefore, when you make sort of case analysis, there's going to be not 2 main cases, but 3 main cases. One case, the original problem starts here, and then new problem also remains here. The second case is, as I discussed, original problem starts here, and the new problem also remains here. And then the third case, original problem starts here, and then moves up to here. These are all the only 3 cases. And then within those cases, obviously, there are a bunch of different sub-cases. All right? The bottom line is, the proof is definitely longer, but as I said, the logic is going to be very, very similar. All right? Just follow the path. Trust me, it's going to be a very good exercise.